For our project, our team, made up of Sam Cantwell, Tate Staples, Cale Vorwaller, and McKay Macarello, chose to create a self-balancing Segway system. Our Segway is a two-wheeled, self-stabilizing robot that uses real-time feedback from an NPU 6050 sensor to maintain an upright position. The system uses a closed-loop control to dynamically adjust the Segway's upright position and respond to changes in balance. With this setup, the Segway can not only stabilize itself, but also perform forward, backwards, and turning motions through user input on the Simulink interface. When a directional input button is pressed, the motors respond by moving in the corresponding direction at a constant speed, for as long as the button is held by the user. The Segway is controlled by an Arduino Uno, 2 H-bridges, an NPU 6050, and 2 DC motors. The Segway motors are powered by a 3-cell LiPo battery and the Arduino Uno board by a 9-volt battery. The NPU 6050 sensor plays a critical role in keeping our Segway balanced. It combines data from both a gyroscope and an accelerometer to accurately measure the pitch angle in real time. Using sensor fusion, the NPU 6050 delivers a pitch angle that minimizes gyro drift and accelerometer noise. This gives us reliable feedback through the Segway's movements. The pitch angle data is sent to the Arduino Uno, where it's used in a closed-loop control system. The Arduino processes this information and converts it into precise control signals for the 2 DC motors, allowing the Segway to adjust and maintain its upright position. Due to hardware limitations, the setup doesn't incorporate encoder feedback or closed-loop velocity control. Regardless, the system still successfully demonstrates the ability to respond to user input and perform basic directional movements and keep itself balanced. Through PID tuning, we're able to adjust the performance of the Segway. Our model, before tuning, was very jittery and inconsistent with motion. After spending much time adjusting the proportional, integral, and derivative gains, the Segway was tuned to what you see now.
Here is our Simulink model for the self-balancing Segway. On the left, we have our pitch angle from our NPU 6050 sensor. That is fed into the summing junction block for desired pitch angle and angle offset. After that, it goes through this PID block, which is there for tuning the responsiveness of the motors for speed and direction with these MATLAB function blocks. In the middle, we have a MATLAB function block that deals with our button presses to determine the right speed and direction. The closed loop portion of our Simulink model for our self-balancing Segway comes from the NPU 6050 sensor reading the pitch angle that changes when the Segway robot is tilting.
While the Segway performed well, there were some limitations in the current design. Using an Arduino Uno restricted our ability to fully integrate encoder feedback into the control loop. This was mainly due to the limited number of interrupt pins, which are essential for accurate encoder readings. The lack of wireless communication meant our control interface had to remain tethered to the Segway for user control, limiting its range and flexibility. Additionally, the cable used for control was also used during tuning and other corrections. This created issues as the cable has a significant enough weight and rigidity to affect the system's performance at times. This led to difficulties in tuning the system, as the setup while wired performed noticeably different depending on how the wire was positioned. Looking ahead, future versions of the Segway could benefit from a more advanced microcontroller with additional capabilities and an integrated wireless module. These upgrades would allow for smoother motion, enhanced autonomy, and a more user-friendly untethered control experience.